We're now going to learn the shocking truth about electrochemistry. Our approach here will be to review some topics in introductory chemistry and then build upon those and understand electrochemistry in more detail. This is typical in chemistry. You learn a topic on one level at an introductory level, and then when you take an advanced course you learn it again, although on a deeper level. All right, let's first review some topics in introductory chemistry about electrochemistry. All right, let's consider a redox reaction. Redox stands for oxidation reduction, so really it should be called an oxide reaction. Here's an example. If you take some copper in solution as copper 2+, and into that solution you put solid zinc, what happens is that copper plates out on the zinc, and zinc then goes into solution as zinc 2+. This is an oxidation reduction reaction. Electrons are transferred from the zinc to the copper. What's oxidized? The thing that's oxidized is the substance or the species that increases its oxidation number. Zinc has an oxidation number of 0. It goes to +2. Therefore, zinc is oxidized. What's reduced? Well, that's the species that has a reduction in the oxidation number here, +2. Copper goes to copper 0, so copper is reduced. What's the oxidizing agent? That's what causes something to be oxidized by itself being reduced. So copper 2+ is the oxidizing reagent. It oxidizes zinc to zinc 2+ by transferring or by accepting 2 electrons, and it itself is reduced. And what's the reducing agent? Well, that would be zinc, because zinc reduces copper to copper solid by giving it 2 electrons, and it itself then becomes oxidized to zinc 2+. All right, so that should, I hope, sound familiar to you from introductory chemistry. Here's some other concepts. Here's the overall reaction, but you can divide this reaction into 2 half reactions where you explicitly show where the electrons are going. So here's the 2 half reactions here. One is a reduction, that's copper being reduced to copper solid, copper 2+ to copper solid, and the other is oxidation. Here zinc is being oxidized, and here we explicitly show that 2 electrons go on to the copper to reduce that, and here 2 electrons are produced from the zinc when you oxidize zinc. So it's an oxidation reduction, and you add these 2 half reactions together and you get the whole reaction, and you do this in a balanced sort of way so that the number of electrons that are going on to the species reduced is equal to the number of electrons that are given up by the species that's oxidized. All right, I hope so far so good. One last slide here to review some electrochemistry concepts. There's so as we had here, we had 1 reduction and 1 oxidation, but in order to do calculations and calculate cell voltages, you write everything as a reduction reaction. So here's the reduction reaction for copper 2+. Here's the reduction reaction for copper or zinc 2+. And each one of these has what's known as a standard reduction potential. That's E0 for copper 2+ and zinc 2+. And in order to calculate the cell voltage for that, you take the standard reduction potential for the species that's being reduced. Here's the overall thing, so copper is being reduced, and subtract off from that the reduction potential. In other words, the reverse of this reaction, reduction potential, the thing that's being oxidized here. And let's just do that for this. So we'll look up in a table what the standard reduction potentials are for copper 2+ and for zinc 2+, and we'll do this calculation. All right, so here is a list. Go back up here. Wikipedia, standard electrode potential data page. All right, so we go down here. We have as a whole bunch of reduction reactions. So see, electrons are being put on various things to produce the reduced species. So these are reduction half reactions, and this is a very negative value, the most negative value here, trying to put an electron on strontium+. That's very unfavorable. It has a negative reduction potential. If we go down to the other end of the table, what we find here, let's look at this one. put an electron on fluorine, that has a very positive reduction potential. So fluorine likes to have an electron on it. It's highly electronegative and so on. All right, so let's see if we can find copper here. See, I already looked it up here. Copper, that's almost right, except here copper is only accepting 1 electron, and we want copper to accept 2 electrons. So we'll go down one here. Here it is. So the standard reduction potential for copper 2+ to go to copper solid is 0.340. There's that right there. Let's look at the standard reduction potential for zinc. Let's see, zinc. Here it is. Zinc, you put 2 electrons on zinc 2+, you make solid zinc. I guess it's this one down here. This one is amalgamated with mercury down here. 0.7618. All right, 0.76, that should be a 118. And so you take the reduction potential of the thing that's being reduced and subtract off the reduction of the thing that's being oxidized, and you get the cell voltage 1.103. All right, so that's a brief review of some introductory chemistry concepts that will be useful later on in electrochemistry. All right, now we're going to look at electrochemistry thermodynamics. How are we going to take into account electrochemistry, or why, in fact, do we need to take into account electrochemistry and thermodynamics? Well, redox reactions, the electrons move. They move from the species as being oxidized to the species being reduced. So electrons are being transported. And if you put in separate containers the oxidation reaction and the reduction reaction, you can have these electrons not being transferred on a molecular level, like when you put zinc, solid zinc into copper 2+ solution, but you can have these electrons being transferred over a wire. And if you connect that wire to, say, a light bulb or an electric motor, then you can do electric work. So that is how we're going to introduce electrochemistry into thermodynamics. We're going to consider the work done in moving electrons from one region of high potential to a region of low potential. In other words, we're going to look at electrical work. Okay, this may be familiar from introductory physics. This is how you calculate electric work. You have a potential. Phi is the electric potential. And Q is the charge. So if you move charge through an electric potential, you do electrical work. If we look at our usual diagram here, this will be electric potential versus distance. So here, if you have a potential gradient over space, say at this region of space you have high electric potential, this region of space you have low electric potential. What will happen if you have an electron in a high electric potential? It will flow down to the region of low electric potential. For example, if you have a battery, one end of the battery is high potential, the other is low. So if you hook up that battery to a wire, you can make electrons flow from the high potential side of the battery to the low potential side of the battery. This is an intensive variable. This corresponds to a potential, and the gradient in potential will lead to a flux of an extensive variable. In this case, it's electrons, or more generally, it's charge. If you're physicists, but we're chemists and we're interested in electrons. All right, so this is how you do electrical work. But as we said, we're chemists and we're interested in number, atoms and molecules and moles and so on. So here, N will correspond to moles of some, we're going to use the ions. So note, we make a note there that these reactions here have charges, and charges, when you move them through a potential, will do electrical work. So far we've not considered charges. All the species we considered so far have been neutral, but now we're going to consider charge, and with charge you have the potential to do electric work. So here's a number of moles of ions. Those are things that carry charge, and this is the Z corresponds to assigned charge signed mean positive for cations and negative for anions. For example, here Z would be +2. If you had something like sulfate, Z would be -2. And finally, if you multiply the signed charge on the ion by the number of moles of ions, that would give you the moles of charge, or moles of electrons actually, because if you have 2+, that means you've taken away 2 electrons. So these are the number of moles times the charge, the signed charge on each ion, will give you the number of charges. But what we want in order to calculate electric work is the charge. So we need a proportionality constant between the number of charges and their actual charge. And that's what Faraday is. That's what the F is. F, which is called the Faraday, named after Faraday, who looked at electrical stuff back in the 1800s or 1700s maybe. The Faraday gives you the proportionality constant between charge and moles of electrons. All right, so there's a conversion factor. So if you take the number of moles multiplied by the ions, multiplied by the charge in the ions, multiplied by the Faraday, then you get the total charge that you're now going to move through an electric potential. And the unit of charge is a coulomb, abbreviated C. All right, so that's how we're going to do it, is review some concepts in introductory physics about work. We're just going to add work. Okay, how are we going to do that? Well, we're going to get a new master equation which contains electrical work. All right, so just to review, how did we get that master equation of chemical thermodynamics? Well, basically we started with the first law of thermodynamics, du is dq plus dw. Then we started to put some constraints on work. So first we said dq minus p dv, that was only PV work. Then we said, oh, how about chemical work? So now we have dq plus p dv plus chemical work. And chemical work, we said, was the sum over, for a chemical reaction, for example, the sum over products and reactants of the chemical potential times dNi, chemical potential of that species. So this was PV work plus chemical work. And now what we're going to do is to add on to this, guess what? Plus PdV plus the sum of the chemical potential. Now we're going to add on electrical work. So it'll be the sum over all the ions that are in the system participating in the reaction of the potential of that experienced by that ion times the charge. And remember, the charge is ZFDN. So if we put a charge of ZFDN through potential phi, we do electrical work. So now we've added on to work, PV work, chemical work, and PV work. And electrical work. Okay, so that's how we're going to introduce it. So now if we just go ahead to the ... remember we got the master equation for chemical thermodynamics. You might want to review that, but we'll just write it down here. dG is minus S dt plus V dP plus the chemical work, sum over I of mu sub I dNi, plus the electrical work, sum over I of the charge ZF times the potential dNi. We can simplify this. There's a dNi there and a dNi here, so we can pull that out, and that'll be just minus SDT plus VDP plus the sum of mu I plus ZF phi, these are all i's, dNi. And let's call this by a different symbol. We'll call this mu I with a tilde above it, and we'll call this the electrochemical potential. So written with that new notation is minus S dt plus V dP plus the sum over I of the electrochemical potential of I dNi. So it wasn't so bad to include electrical work. All we did was include the electric potential and the electrical work and the chemical work and give it a new symbol, mu tilde I. So there it is. There's the master equation for chemical thermodynamics, in which we included electrical work, which we have to do if our system contains ions. Okay, so that's that. Now let's look at what's going to happen at constant temperature and pressure. So constant temperature and pressure, constant temperature, that goes away, constant pressure, that goes away. The incremental change in free energy when you add a certain number of moles will just be the sum of mu I dNi. Again, exactly the same thing we had before, except now we're using electrochemical potential instead of chemical potential. And let's consider one more thing. At equilibrium, we have dg is equal to 0, and therefore we end up with exactly the same thing we had before. Maybe the sum of all species, and let's look at a chemical reaction, of the sign stoichiometric coefficient of that species times the electrochemical potential of that species has to equal 0 for reaction. And again, recall that this is the signed stoichiometric coefficient in the balanced chemical reaction. So there it is at equilibrium. Okay, so that wasn't too bad. All we do is substitute the symbol for mu, substitute for mu the symbol mu tilde, and everything we said before about the master equation of chemical thermodynamics and equilibrium and all that stuff is the same, except now we're using electrochemical potential. All right, that wasn't so bad. So now, next lecture, we're going to talk about EMF, electromotive force, the Nernst equation, and membrane potential.